Now, today is the last lecture that I will give. On next Monday, there will be Frank, who most of you know from the introduction course, who gave then a lecture on representation. He will be talking about philosophy of mind. So, questions about what is the relation between human intelligence and machine intelligence? What are the restrictions of the artificial mind, and so forth. And in the years that I've been here, these were always fantastic lectures, so I really recommend you to come. I will also spend a little bit of time in the second half today on questions of ethics. So as we have had a bit of problems with the right level sometimes, so we have fewer time than we wanted to have on the ethical issues. But I still want us to take some time to reflect on what we are doing here as scientists, in particular scientists in artificial intelligence. So I don't want to ignore that completely. So we spend a little bit on that in the second half today. These questions, both the philosophy of mind and the ethics, will both be also part of the exam. So there will be questions on philosophy of mind and questions on ethics. There is no right and wrong answer in ethics, of course. So that's the problem with ethics, is that it really comes down quite often to conscious decisions that you have to take in morally difficult situations. So you will not be judged on the one or the other judgment you would make, but on the arguments and also on the fact that you have reflected on some of the issues that were mentioned in the lecture. Yeah, but I want to start with the logic to wrap up what we did in the past two lectures. Remember that we had these agents that we normally had just execute some systematic search through the search spaces, and now we also try to come up with a formal way, a generic way, in which we could deduce new facts that were sort of implicitly modeled in the knowledge base. And with this very simple game of Wumpus, I think we have seen already how this works and how we would benefit from this. And yesterday I tried to explain some of the basics of the formal semantics and introduce the first calculus with Davis-Putnam. Today we are seeing two more different ways of doing exactly the same thing. So a calculus for entailment or for satisfiability. And then, as I said, I will move to the ethical questions. And of course, we only really touch very superficially at these automated reasoning methods, Davis-Putnam, rule-based reasoning, and then resolution. And all I want you to understand is that there are different paradigms for doing the same, and that they are sort of the automation of those semantic notions that we've seen yesterday. So that's the plan for today. I want to start with something I think yesterday could have been a little bit confusing, and that is the relation between entailment and satisfiability. And all the motivation was we have a knowledge base and we want to check whether certain facts follow logically from those knowledge base, so whether these facts are entailed by the knowledge base. And then I switched maybe too fast to the question of satisfiability as the reasoning task at hand. And the relation between the two is that if we want to prove entailment, so we have a knowledge base and we want to check whether a certain formula, a fact, follows logically from this knowledge base, so whether KB entails phi, then it can be shown, and it has to, of course, be proven, but we don't do that here, but you have to trust me on that this comes down to exactly the same thing as to say we just add the negation of this formula to the knowledge base. So this has to be then a set. So this is the union sign that Michael also introduced. So this means this is a set of formulae, and this is a set with just one formula in it, and we just put them together into one new set. Yeah, so that was the set theoretic notion that you've learned 2 weeks ago. So we take all the formula in the knowledge base, we take a new formula, namely the negation of the one that we want to show entailment for, and then we show that this one is unsatisfiable. So that's important, that it must be unsatisfiable. And this is, again, so I shouldn't use, so this means that we prove that it is unsatisfiable. I should just use natural language, is unsatisfiable to avoid confusion. And this is the same as there is no model. No model for this plus the negation of phi. Yeah? Yes?
On the slide, is there the little squiggly line in the A? Is that not psi?
Yes. Yes. So this is the same. And I mentioned that before, and I tried to bring it, take it out of the slides, that for these languages, these language models, these propositional logics, but all logics you will see, there are always different ways of writing that down. And there is no consensus on how to write propositional logic. And sometimes you use the wiggly sign, sometimes you use this, sometimes you just also see this. And the attempt in this course was to have it consistently with this symbol, but this one wiggled its way in. Yeah. So the more you work with this, the more natural it becomes that you use different symbols. So, for example, you will also see that for this symbol, I will use sometimes this. This is the end, and this is also an end. This is just supposed to mean the same thing. But this shouldn't have happened, so apologies for that. So the core thing here is that we want to show entailment. And there is some reasoning methods that are not sort of built for that. And the two that I showed today, or the three that I showed today, particularly the first and the last, they are not made for entailment. They are made for satisfiability. And remember, what we did last time in the second half was to look for models as a search with the search algorithms of David Putnam. And of course, then basically what you do is you find a model. And at the moment that you find a model, you have a counterexample against this, because, and that basically means that this is not entailed. Yeah? So if you find a model, it's not entailed. If you do not find a model, it's entailed. So this is the procedure that you have to follow, and it's simply another algorithm you have to just know. It's a cookbook recipe. You start with your knowledge base. Yeah? If you use an algorithm that's sound and complete, then it is not possible. So that's really the property of these calculi, that you find all the models. And if you don't find one, you are sure that there is none. So that's the property of the algorithm. And if you employ an idiotic algorithm, then you don't know. But there's also, I mean, it's a very interesting comment, because if you have too many variables and the problem becomes too complicated, you can also use heuristic algorithms like we did in the search in the first 2 weeks. And some of them, if you use them I don't know which one we had, the beam search, for example, where you only left a part of your search space in the in memory, or hill climbing, of course, will not find all models. So if you employ one of those algorithms, they might be very quick in finding a model if there is one, but they might never ensure that they have looked at all the possible models. Yeah, so these are then approximate algorithms or incomplete algorithms. And whenever you have a problem where you know that probability that there is a model is very high, then these incomplete algorithms might be very useful and very powerful. Okay. So what I've forgotten to say is that the algorithm that we're seeing now, particularly again the Davis-Putnam in most cases and the resolution, the last one I show, they depend on the formula being in this closed normal form, in the conjunctive normal form. So what you have to do first is to translate the knowledge base, so your formula in the knowledge base, into closed normal form. Then you have to take the negation of the formula that you want to prove entailment. Again, you transform this negation, don't forget the negation, into closed normal form. And then you add the negation of this to the closed normal form of the knowledge base, which gives you another closed normal form. And for this closed normal form here, these two, you then apply your Davis-Putnam solver or the resolution solver. And if this one tells you there is no model, that means that the search is exhausted, then it's unsatisfiable. And if the model is found that it's satisfiable, and it's satisfiable, it's not entailed. So that's the sort of maybe a bit counterintuitive thing, but that's what you would always do in assuming the opposite in order to prove the thing itself. We as humans do that also. Because we assume the opposite in this line 2, that's where we turn the logic around. So that's a procedure you also just have to learn. I can promise you that if you don't know this slide, then you will have fewer points in the exam than if you know the slide. I don't think I can say it more subtly. Okay, let's go more into Davis-Putnam again, because at the end of yesterday we ran out of time and steam, I guess. And basically the general idea was that we have our formulae knowledge base in closed normal form. Maybe not necessarily in closed normal form, but it's better to have it in closed normal form for DPLL. And then you just choose a variable and you assign a truth value to it. And in the exam, if we do that, for example, we might give you some rules how to do this. So start alphabetically and assign falsity first. But in principle, when you implement your algorithm yourself, this is a moment of choice. And of course, the next step is that if you want to do this efficiently, you should choose some kind of heuristics. We're looking into that in the next slide. For the moment, it's important that there is some tricks that make this Davis-Putnam search procedure efficient. Because if you really do it in the naive way that you assign a value to one, you check whether you satisfy all the formulae or not, or whether there are no formulae left to satisfy. And if you don't have an answer to your question, basically, you just assign a next value. So you work with these partial assignments that you make more complete step by step. And if you find a contradiction, you do the backtracking thing. But now we have things where how we can improve the search, basically cutting the search tree and only looking at very few places. And that is the early termination. So if any literal is true in it, then we can remove the clause. And if a sentence is false, if all the clauses are false, then we can return false. So we can do this check in the beginning of the step, of each recursive step. We can also do some more heuristics, and the most powerful one was the unit clause heuristics, that we always start with a clause where we only had one literal, so one atom that was either negated or not negated. Yeah. And then to put this all together, we get this algorithm that I don't want to go through detail now because we have seen all the little steps we have seen, and just have to go through them one by one to understand, to have the full Davis-Putnam algorithm. So then the question is, does it always give the right answers and give all the right answers? So soundness means that if the algorithm says it's satisfiable, here is a model, then this is indeed a model that it finds. And complete means that when it runs through the whole algorithm and it hasn't found a model, there is indeed none. So that was related to your question. So these are the properties of Davis-Putnam. And because we only have a finite set of variables that we can assign values to, we also terminate, because we can only have 2 to the power of n possible variable assignments. And this is what Davis-Putnam does. It goes through all those like the truth table do, but in a more efficient way. So this is what I said before. It only does satisfiability. It doesn't do anything else. So if you want to show entailment, then you have to do this trick of either adding, if not base is a formula, then you just conjunct it with the negation of alpha, or if it is a set of formula, you have to add a set with this one formula. Okay, so let's do an example, because this is something, again, that you should be able to do in the course. And here is a formula. And let's start with the first variant where we use the alphabetic order, and we start with falsity first. So take 30 seconds, half a minute, and see what we should do here. Okay, yeah.
Is there any reader or prep coming for these lessons? Because on the campus there's nothing so you can read it. There's only the slides.
There is also the reader from last lecture where this is included. For the first lecture on the predicate for the propositional logic, I thought it also covers Davis-Putnam. It might not be, so I'll check it. Yeah, sorry. I'm sure that resolution is also in the book. Maybe it's not in the 8 pages. I thought everything was in these 8 pages that I gave for one of the previous lectures, but I'll have to check it. Sorry. Yeah. Anyway, so can we still? What do we start with? What do we have to do? So now we're looking for satisfiability. So we're not doing all this entailment translation step first. If you look at the formula, it is already in closed normal form, so that's fine as well. So all we have to do now is start with a variable assignment. And as I said, we start with a variable assignment in alphabetic order and falsity first. So that already tells you exactly what you should do. We start with variable p and assign falsity to it. Yeah? So now we are in a new state. And can you now tell me what happens with the clauses? So what do we have now in our knowledge base after we do all these pre-processing steps that I've talked about? So we know P is false.
We know the flash clause is true.
Exactly. Yes. So the first one is true because here we say P is false, and here we say Q must be true, or R must be false, or P must be false. We know P is false, so this clause is satisfied. So we can just delete it. We don't need it anymore. So we move to the next one. How do we transform the next one? We know P is false. So what is left of this formula? No, it's not false because something or false is true if this something is true. So you basically delete the P, and we just have to write not R or Q, because that's the first clause that is left. So the very first one is deleted, and from the second one we can delete the P. Yes? That was my choice.
Oh, okay.
And I had to do it. I had to take this choice because of the alphabetic order. So P, Q, R, P is the first. And I had falsity first. So that makes it P is false. Yeah? So then what happens to the third one? Nothing. P is not evolved, so we just have to keep it. So R or Q. What happened to the last one? No, there's a P. The P is false, so we have to delete the P. So we retain the not Q. Yeah. So the algorithm is very simple. You decide on P to be false, and then whenever not P occurs in a clause, you delete the clause, and whenever P occurs in a clause, you delete the P. These are the two things you can do. Yeah. That's the most important thing you have to understand of this algorithm. Okay, so now, is this true or not? No idea. Yeah, so we have to continue. What's the next step? We are doing alphabetic ordering. So which variable are we choosing? And we use again falsity first. Yeah. So what happens now to our clauses here? So this one we can delete the Q. So the next step is not R, and here we have R, and this one is true, so we delete it. We don't need to take it into account anymore. Yeah. So in this step now, we have two more clauses left, not R and R. And of course, if you now choose R to be false, so this is now our R. So if it's false, then we have a contradiction. And if you use true, it's also contradiction. Yeah. So basically, this means this one was not correct. We need to do backtracking, and we need to check what happens if Q is true. But this was this step. We're now going back to this knowledge base, and we see that Q is true is not a good choice either. So that gives us a contradiction immediately here. Yeah? Yeah?
Couldn't we see that all in the step because we have Q and not Q, R and not R? In the step before.
So basically there is this additional rule where you have the unit clause, where if you have a unit clause here, you know that you don't have to do this anymore. So that is the one step where I forgot one of the rules of Davis-Putnam. So you could have already said there is only one possibility, and that is F has to be false here. And then you get the clash here immediately as well. So this one is probably indeed unnecessary if you follow the unit clause. So then we have the alternative that we need to do the backtracking to A to be true, to P to be true. And then we get a new knowledge base here. This one can go. So what is the knowledge base we have now after making the choice that P is true? What is left of the first clause? Yeah, so that is Q or not R. What is left of the second one? We just delete it because it's true automatically. We keep the third one, which is not R or Q. Sorry? Oh, sorry, it's R. And the last one is deleted again. Yeah? Because P is true, so it's not constrained. So now we'll go to the next one in the alphabetic order. Test what happens if it is false. While I do this now, I can also say, yeah. We're still on the first. We're still doing the backtracking. We haven't found a model yet. We'll find a model very soon. So there is also the rule that is called the what was the name of it again? So the pure literal. Basically, what you see here is that that Q occurs in both positive without a negation sign, and whenever that happens, you can just choose whether Q is false or true, because you will never have a contradiction anymore. So basically, if you find this, you know that whatever you choose for Q, you will have a model. So that's the, you can basically delete those clauses. So that's a specificity of this pure rule. But if you don't do that in the lecture, don't worry about it. But that would also help you. Let's say we choose Q to be false. That obviously doesn't help us. So we have to do Q to be true. And then we get, we find a model. Because then it doesn't, I'm sorry, what I say is nonsense. I have to do it properly. So if you decide Q to be false, then this one goes and this one goes. No, sorry. The first one is true automatically. Yeah, if you choose. No, we have to check both of them. So we are left with not R and we're left with R. Do it step by step, not jump ahead too much. So we get not R and we get a contradiction again. And if we choose Q to be false, then we now delete both clauses and we found a model.
Can we say that because we have R and not R in both clauses, then it depends on Q what the result will be? If Q is
I don't understand what you mean.
because we have R and not R. So
Yeah.
if R is true, then the other one will be false. So it only depends on Q.
Yeah, so this is basically the resolution calculus that we have seen in 20 minutes or so. Okay, so that was variant 1, where we basically find a solution here. Yeah?
Do we still have to do all the steps if we already see like the only solution? Or like in this case, for example, you see that Q is true is the only, like, is the model. So can you just assume then because you can eliminate them easily?
Yeah, I would just write it down like a machine, because what we do here is applying an algorithm, and the machine wouldn't jump ahead unless you have some clever method, like we are trying to do now. Because now we are applying a heuristics for the same thing, and that is the heuristics that's called the MOM heuristics, and that is the most occurring in the minimal clauses. So which are the minimal clauses, the smallest clauses? The last two, yeah. Which is the variable that occurs most often in the last two clauses? Q. Okay, so we start with Q. And we start with falsity again, because that was the assumption that we had in our algorithm. But in the interest of time, I would suggest we immediately move to the third variant. So this now, you just follow all the steps and do exactly the same what we did before, only that you don't choose those alphabetically anymore, but you choose them now by this MOM heuristics, most occurring in the minimal clauses. And if the clauses are the numbers are the same, then you do a random choice or something like this. We're now looking at a way of implementing this efficiently. Yeah. So let's go to the third variant, and I've called this heuristics of more negative or more positive occurrences. So if in the whole data set, the Q, which we choose first, so we first choose the variable, and now we choose, do we start with the falsity or do we start with the positive, the truth? And now if my heuristics is if Q occurs more often with a negation, then we start with false. And if it has more often not a negation, then we start with true. Yeah. So with what would we start here now with, according to this heuristics? True. Yeah. So we would start with Q is true. Sorry. No, it occurs more often with without the negation. So we give it this as a value of true. And the reason why we do this is, of course, that then we can delete the first three clauses immediately. Yeah. So basically, our heuristics tells us start with the Q because it occurs in these two most often. And the second part of the heuristics tells us start with Q being positive because then we can delete most clauses immediately. So if we start with Q being positive, what is left? Just the last one and just this. Yeah? And then the next step is, of course, that P must be true. So basically, instead of having the whole tree now drawn, we only have 2 clauses left in order to find the model. Here we see again the power of the heuristics that can help us to reduce the search space enormously. Yeah?
Like when the occurrence of something is similar, like it's the same, essentially, it's equal, do we do it alphabetically then, or?
So there is no right answer here. The point is that if you implement this algorithm, you have to make a decision. And you can say, do it randomly. That might be the easiest one to do. It might be take the first one that's in your data structure. I just say here, do it alphabetically, because then if you write an exam, then I get all the same calculi and not 215 different variants of the same idea. So that's why I say do it alphabetically, because then all my trees look the same. But in the real implementation of this, you would make it as easy implementation-wise as possible, or use the heuristics here. Okay, so that's Davis-Putnam, and that I think shows very nicely this example what the power is of these heuristics. And then I made a mistake yesterday when I talked about the complexity of Davis-Putnam as compared to truth tables, because I'm probably you didn't notice, but I said that the complexity would go down from 2 to the power of 7, which was the number of variables, and it would go down to the 2 to the power of 5 or 4 or so. That was incorrect. The potence stays the same. What changes is the base. So we are not reducing the 2 to the power of 7, but we are reducing it to 1.5 to the power of 7. So it's the number of variables that still determines the exponent. And nothing can change that in Davis-Putnam or in any search procedure. This would sort of, this has been proven not to work. But what changes is the base. And if you think of a problem where we have 50 variables, so if you, for example, would model the Wumpus world, you have already the 16 board positions, and for each of those board positions, you would want to know whether there's a breeze and a Wumpus and a pit and so forth. And I think we had 10 or 15 or 20 different propositions per position on the board. So if you have 16 times 10 already, then we're talking about 160 different propositions that we would like to work with. But then you see already, even if you only work with 50 propositions, the search space that you have to look through is enormous. And if we apply a good algorithm such as Davis-Putnam with good heuristics, then this can be reduced significantly by 5 orders of magnitude, but still it's enormous. So this remains a big problem in reasoning with these systems. So this was the paradigm of searching for a model. Now we're looking at a different paradigm, and this is the paradigm of the rules that we have and whether we can rewrite formulae into other formulae. So how do you do that? You use inference rules, and these inference rules can be written down in many, many different confusing ways. We have had this with the negation sign first, but so you can write down there's an equality between the two things. So if I have a formula A implies B and A, then write B. Here you see also that I use the other and symbol. You sometimes see it written like this. So if we have A implies B and A in my set of formulae, then derive B. So you put it underneath. The whole idea is always the same. So you have a set of formula A, or in this case, one formula A, and you can derive a new formula B out of this. So these are the rules, the inference rules of propositional logic, the main ones. And that is that the modus ponens rules, if you have an implication and you know the first argument of the implication, you can derive the second one. Yeah, so if I know that A implies B and I know A, then of course I can also add B to my data, my knowledge base. So I can just add new information. The next one is called AND elimination. So if I have a conjunction, then I can derive both of the conjuncts. So we did very similar things yesterday in the lecture, where we sort of said that the next thing that A is entailed by A and B. But here we're now talking about an algorithm that we write. We have symbols, A conjunction sign B, and now we can derive something, we can add something new to our database. So that's an implementation thing, that's an algorithmic thing. And then we can write down logical equivalences that we have already seen. For example, this one, that alpha and beta, if they are equivalent, then that means that they imply each other in both directions. And then there is a set of those equivalence rules for rewriting. So, for example, we can rewrite a conjunction in the conjunction in the other direction. So, alpha and beta can be rewritten into beta and alpha. The same holds for disjunction, and we have several of those rules. And some of those rules you have already seen that for rewriting into closed normal form, if you choose a subset of those rules and you apply them in the right order, you always end up in closed normal form. There are more of those rules, and basically what you can do is with these two rules above here and this set of equivalences, you can rewrite any propositional logic rule knowledge base into a knowledge base that contains the formula that you want entailed. So basically, I could take all the rules of the game of Wumpus, and I can manipulate all the formula again and again and again and again and again until I have the formula that is entailed in my knowledge base. Yes? You get those rules in the exam for the rewriting of the closed normal form, but you do not have to do reasoning with this, so the free reasoning with rule-based reasoning in the exam, because this is, if you think about it, the next step of what I wanted to say is, this becomes now a search problem again. Namely, you have a knowledge base and you can apply rules to it. Which rule do you apply? And basically, you have the two on the previous slide, and you have those 15 here. So basically, you start out with a search tree of 17 possible actions you could take. Even more, because all the alpha and beta stand for different formulae. So it could even be more. So your search basically begins with 100 options. So if I ask you in the exam to do this, and you get lost in step 1, you will never find it, and you will need the whole time for the exam and find nothing. So this is nothing to do in an exam or also by hand. It's just an idea of how you can also solve the problem of entailment by just rewriting a knowledge base with these rules into another formula. And when you manage to rewrite it, and it's a simple search problem, so you can implement this easily in a heuristic search that we talked about in the first weeks, and then you have your reasoner for entailment. And basically what has been shown again is that if you use this set of rules that I'm shown here, then you get again a sound and complete calculus, which means that you can derive every formula that is entailed by just rewriting. And whenever a formula is not entailed, it cannot be rewritten. Yeah. So people say this is a complete axiomatization of propositional logic, because by these formulae you can derive everything that's true in propositional logic and not, just by searching for a rewriting procedure from the knowledge base to the thing that you want to show is entailed. Yeah. So here's an example of how you would do that. We have the Wumpus world knowledge base, And now we just go and search for all the possible rules we could apply. So for example, we would find the biconditional elimination. That's one of the rules here, biconditional elimination. So the equivalence is rewritten in, like you do in the procedure of closed normal form. And basically you rewrite step by step all those formulae into using, for example, the modus ponens rule I had before, and the De Morgan rule I had before. And basically then you can derive that there is no pit in 2.1, which we had done previously with Davis-Putnam, or which we had done shown you that this is what is entailed. Yeah. So this has been a simple rewriting procedure from the knowledge base by these rules, applying these rules until we come to the conclusion we want to prove. And obviously, the same as we did in the search procedures in the first week, you can now do that, for example, in different directions. That's the next slide. I thought it would be this one, but there's one more information. The nice thing here is that we do not have to do anything clever. We can just take the things that we rewrite and add. So our set gets bigger and bigger and bigger and bigger. It can be shown that when you apply a rule, the new formula that you add will be shorter. So that means that after a long time of applying, your formula gets shorter and shorter and shorter. And at a certain point, this stops. So we terminate. We cannot do this infinitely long rewriting. So that's the termination condition. And it has been shown that each of the application of the rules always produces valid things that are really entailed. So this is why we have a complete and sound and terminating algorithm. Again, it's a completely different idea like the Davis-Putnam. I hope you understand that. And that's what I wanted to convey here. I want to spend the first 10 minutes of the second half on resolution, which is a far simpler version of this application of the rules. For now, I take this out of it says here do it, but as I said, this can become very nasty and complicated. So we're not having this in the exam. This is a full rewriting calculus. For languages like the ones that Frank was talking about in the introduction course, and for the knowledge graphs, for example, this is really the method of the standard method of doing reasoning. For propositional logic, people use Davis-Putnam. And for more expressive languages, they use the principle of resolution, which we're going to look into in some minutes. The final thing, that's what I wanted to say when I forgot that there were 2 more slides in between, is that, of course, now you can, again, do this two-directional. You can say, I start with a knowledge base, and I try to derive and rewrite my formula, which I want to show is entailed. But I could also do it the other way around. I start with my formula, and I try to reconstruct the knowledge base. So you also, again, have the data-driven and the goal-directed, the goal-driven search paradigm. So I wanted to show you this in order to show you how close this all is related to what we did in the first 2 weeks. So Davis-Putnam is really a search through directly through the models. This rule application is really a search through possible actions that you could take by choosing a specific rule to apply or another rule to apply. Yeah? And then let's have 10 minutes break, start at 12, and then I will do very briefly resolution before we discuss some ethical questions.